Tonight, I'd like to tell you about one of the big questions in science. It's a question that goes back at least 2,500 years to the ancient Greeks, and it's a question that has been discussed in this room many, many times over the past 200 years, but it's an important question, and I think it's important that we revisit it. And the question is simply this, it's what are we made of? What are the fundamentals as they appeared? So if you look closely at light waves, you'll find that they're made of particles. They're little particles of light, and these are particles that we call the photon. Okay? The magic of this idea is that that same principle applies to every single other particle in the universe. So there is spread everywhere throughout this room something that we call the electron field. Okay? It's like a fluid that fills this room and in fact fills the entire universe. And the ripples of this electron fluid, the ripples of the waves of this fluid, get tied into little bundles of energy by the rules of quantum mechanics, and those bundles of energy are what we call the particle, the electron. Okay? All the electrons that are in your body are not fundamental. All the electrons that exist in your body are waves of the same underlying field. Okay? We're all connected to each other. It's like, the waves on the ocean all belong to the same underlying ocean. The electrons in your body are the ripples of the same field as the electrons in my body. Okay? There's more than this. There's also in this room two quark fields. And the ripples of these two quark fields give rise to what we call the up quark and the down quark. And the same is true for every other kind of particle in the universe. There are fields that underlie everything. And what we think of as particles aren't really particles at all. They're waves of these fields, tied up into little bundles of energy. Okay? So this is the legacy of Faraday. This is where Faraday's vision of fields has taken us. There are no particles in the world. The basic fundamental building blocks of our universe are these fluid-like substances that we call fields. And I want to tell you what we can do with that and how we can best understand the universe around us. Okay? So here's the first thing. Take a box and take every single thing that exists out of that box. Take all the particles out the box, all the atoms out the box. What you're left with is a pure vacuum, and this is what the vacuum looks like. So what you're looking at here is a computer simulation using our best theory of physics. It's something called the Standard Model, which I'll introduce later. But it's a computer simulation of absolutely nothing. Okay? This is empty space, literally empty space with nothing in it. This is the simplest thing you could possibly imagine in the universe. And you can see it's an interesting place to be, empty space. It's not dull and boring. What you're looking at here is that even when the particles are taken out, the field still exists. The field is there, but what's more, the field is governed by the rules of quantum mechanics. And there's a principle in quantum mechanics, which is called the Heisenberg uncertainty principle, which says you're not allowed to sit still. And the field has to obey this. So even when there's nothing else there, the field is constantly bubbling and fluctuating in what's, quite honestly, a very complicated way. Okay? These are things that we call quantum vacuum fluctuations. But this is what nothingness looks like from the perspective of our current theories of physics. Okay, it's worth saying that this is a computer simulation. It looks a little bit like a cartoon, but it's actually quite a powerful computer simulation that it took a long time to do. But these aren't just theoretical. These quantum fluctuations that are there in the pure vacuum are things that we can measure. There's something called the Casimir force.